July 1st, 2025. A telescope in Chile catches something extraordinary, a faint streak of light moving through the constellation Sagittarius, racing through space at over 200,000 kilometers per hour. Let's listen and watch. Within hours, astronomers realise what they're looking at. Not a member of our solar system, but a visitor from somewhere far beyond, carrying frozen material that predates our Sun itself. The third confirmed interstellar object ever observed, and potentially the oldest comet humanity has ever seen. A cosmic messenger that's been drifting through the darkness for 7 billion years, now releasing water vapour in ways that defy every expectation. This isn't just another icy rock passing through. This is a time capsule from the ancient galaxy, a frozen archive from a star system that may no longer exist, teaching us that the ingredients for life are scattered across the cosmos in ways we're only beginning to understand. The discovery happened on what should have been an ordinary evening at the Atlas Survey Telescope in Rio Hurtado, Chile. The Asteroid Terrestrial Impact Last Alert System, designed to spot potentially hazardous objects near Earth, picked up an anomalous signal. At apparent magnitude 18, far too faint for the naked eye, a small point of light appeared on the detectors. Initial observations showed it was moving at 61 km per second relative to the Sun, positioned roughly 524 million kilometers from Earth and over 675 million kilometers from the Sun itself. The designation came quickly, A11PL3Z, a temporary identifier while astronomers scrambled to gather more data. Within a day, the International Astronomical Union's Minor Planet Center received observations from multiple facilities around the world. Pre-discovery images started emerging from archives. The Zwicky Transient Facility at Palomar Observatory had captured it back on June 14th, 2 weeks before the official discovery. Atlas telescopes themselves had logged it as early as June 5th, but the comet had been moving through the dense star fields near the galactic center, where it blended into the background noise of countless distant suns. What made astronomers sit up and take notice wasn't just that this object was there, it was where it was going, and more importantly, where it had come from. The orbital calculations told an unmistakable story. This wasn't an object bound to our Sun's gravity. Its trajectory was hyperbolic, an open-ended path that meant it was just passing through, never to return. The third interstellar visitor humanity had ever confirmed, following the mysterious cigar-shaped Oumuamua in 2017 and the pristine comet 2I Borisov in 2019. But 3I Atlas, as it would officially be named, was already showing signs of being different from its predecessors. On July the 2nd, just 1 day after discovery, 3 separate observatories reported the same thing: a marginal coma surrounding the nucleus and a potential tail-like elongation stretching, about 3 arcseconds. This wasn't an inert asteroid like Oumuamua, this was an active comet, already outgassing as it approached the inner solar system. David Jewett and Jane Liu, using the Nordic Optical Telescope, confirmed it decisively. The object was clearly active, with a diffuse appearance that left no doubt. 3I Atlas was releasing material, shedding gas and dust into the void, even though it was still incredibly far from the Sun. This early activity was unusual. Most comets from our own solar system remain dormant at such distances. Their ice is locked in deep freeze until solar radiation warms them closer in. NASA's Transiting Exoplanet Survey satellite had been watching the region where 3I Atlas travelled back in May, 2 months before anyone knew it existed. When astronomers reviewed those archived observations, they found the comet was already bright and active on May 7th, when it was roughly 958 million kilometers from the Sun, about 6 times the distance between Earth and our star. That meant the activity wasn't being driven primarily by water ice, which typically doesn't sublimate at such frigid temperatures. Something else, some other volatile compound frozen in the nucleus, was already responding to the faint warmth of distant sunlight. The James Webb Space Telescope turned its powerful infrared eye toward 3I Atlas on August 6th. What it saw rewrote the textbook on what to expect from interstellar visitors. The spectrum showed carbon dioxide dominating the coma, far more abundant than water. This was a reversal of the typical pattern seen in solar system comets, where water vapour usually takes centre stage. Carbon dioxide, carbon monoxide, and carbonyl sulfide all showed up in the data, painting a picture of a comet with a complex chemistry, one that formed in conditions very different from the frigid outer reaches where our own comets were born. Observations from the Very Large Telescope in Chile added another layer to the mystery. Spectroscopic analysis detected cyanide gas, not unusual in comets, but also atomic nickel vapour at concentrations similar to those seen in solar system comets. Nickel emission had been observed before in other comets, including the previous interstellar visitor 2I Borisov, but seeing it here reinforced that certain chemical processes might be universal, transcending the boundaries of individual star systems. The Hubble Space Telescope captured its first images on July 21st, revealing the coma in exquisite detail, a teardrop-shaped cocoon of dust streaming away from the solid icy nucleus. Because Hubble tracked the comet's motion across the sky, the background stars appeared as streaks in the long exposures, while 3I Atlas itself remained sharp and clear. Those images allowed astronomers to constrain the size of the nucleus, narrowing it down to somewhere between 440 metres and 5.6 kilometres in diameter, with the most likely size being less than a kilometre. But it was what happened next, in late July and early August, that truly astonished the scientific community. NASA's Neil Gehrels Swift Observatory, a space telescope designed primarily for studying gamma-ray bursts and other high-energy phenomena, pointed its ultraviolet instruments toward 3I Atlas. Swift's vantage point above Earth's atmosphere meant it could see wavelengths that never reach the ground, wavelengths that get absorbed by our protective blanket of air. What Swift detected was a faint ultraviolet glow, the signature of hydroxyl gas. Hydroxyl, a single oxygen atom bonded to a single hydrogen atom, is what's left over when water molecules are broken apart by sunlight. It's the chemical fingerprint of water, the smoking gun that reveals active water ice even when you can't see the water vapour directly. And 3I Atlas wasn't just releasing a little water, it was hemorrhaging it. The team at Auburn University, led by postdoctoral researcher Zexi Xing and Professor Dennis Bodowitz, painstakingly analysed the Swift observations. They stacked dozens of short 3-minute exposures, combining over 2 hours of ultraviolet observations and 42 minutes in visible light. The signal was faint, requiring meticulous work to tease it out from the background noise, but it was unmistakably there. The hydroxyl emission proved that water vapour was escaping from the comet. Here's what made this discovery so extraordinary. When Swift made these observations, 3I Atlas was nearly 3 times farther from the Sun than Earth. At that distance, about 450 million kilometres from our star, water ice on a comet's surface should be frozen solid. The temperatures are far too cold for direct sublimation, the process where ice turns straight from solid to vapour without becoming liquid. Yet the comet was losing water at an astonishing rate, approximately 40 kilograms every second. That's roughly equivalent to a fire hose running at full blast, continuously, pouring water vapour into the vacuum of space. How was this possible? The leading theory involves the comet's coma, that cloud of gas and dust surrounding the nucleus. Near-infrared observations from Gemini South and NASA's Infrared Telescope facility revealed water ice grains in the coma, particles smaller than 1 micrometer floating in the debris field around the nucleus. The hypothesis is that these tiny ice chunks, ejected from the surface by outgassing carbon dioxide and other volatile compounds, are then exposed to direct sunlight. Without the insulating layer of surface material protecting them, these grains heat up enough to sublimate, releasing water vapour even though the nucleus itself remains too cold for its surface ice to vaporize. This extended source of water has been seen in only a handful of distant comets from our own solar system. It suggests that 3I Atlas has a complex layered structure, different ices with different freezing points, arranged in ways that preserve clues about the environment where it formed billions of years ago. The significance of finding water in an interstellar comet cannot be overstated. Water is the universal yardstick in comet science. It's the baseline measurement that allows astronomers to compare different objects, to understand how sunlight drives activity, to calculate production rates of other gases. With 3 Atlas, for the first time, scientists could place an interstellar visitor on the same scale used to study native solar system comets. They could begin to make direct comparisons between the chemistry of our cosmic neighbourhood and the chemistry of a completely different planetary system. Dennis Bodowitz put it beautifully. When we detect water, or even its ultraviolet echo in hydroxyl, from an interstellar comet, we're reading a message from another planetary system. We're receiving a note written in the language of chemistry, telling us that the ingredients for life's processes are not unique to our little corner of the galaxy. Water, the molecule that defines life as we know it, exists out there in abundance, frozen into comets that wander the spaces between stars. Every interstellar visitor so far has been a surprise, Xing noted. Oumuamua was dry, or at least appeared to be, showing no signs of cometary activity, and leaving astronomers to debate whether it was even a comet at all, or some other kind of object. 2E Borisov was rich in carbon monoxide, more so than most solar system comets, but its water content was relatively normal. And now 3I Atlas was releasing water where no one expected it, at distances where conventional wisdom said it shouldn't be happening. Each visitor rewrites what we thought we understood about how planets and comets form around stars, expanding the boundaries of what's possible. The question of age adds another layer of profound mystery to 3I Atlas. When the comet arrived in our solar system, it was moving away from the galactic centre with a velocity component relative to the Sun of negative 51 km per second, and it was travelling upward through the galactic plane at 18.5 km per second. That vertical velocity is quite high compared to nearby stars and other known interstellar objects. It meant the comet followed a tilted orbit around the Milky Way itself, suggesting it belonged to either the thin disk or thick disk populations of our galaxy. The thick disk is where things get interesting. This region of the galaxy contains older stars, ancient suns that formed billions of years ago, when the universe was younger and the chemical composition of stellar nurseries was different. These stars have lower concentrations of heavy elements than our Sun, a telltale signature of their age. Matthew Hopkins, a researcher at the University of Oxford, developed a model to predict the characteristics of interstellar objects based on their orbits and likely origins. When he and his colleagues applied this model to 3I Atlas, the results were staggering. With 68% confidence, they estimated the comet is between 7.6 and 14 billion years old. The most likely age, hovering around 7 billion years, would make 3I Atlas 3 billion years older than our solar system, which formed 4.6 billion years ago. This would make it the oldest comet ever identified, a primordial relic from the early epochs of the galaxy. Hopkins described waking up to messages from colleagues. Rather than the quiet Wednesday he'd planned, he found himself bombarded with excited texts. 3I, they wrote, followed by multiple exclamation marks. The comet he'd been modelling hypothetically had actually shown up, giving him a chance to test his predictions on something real and possibly ancient. Chris Lintott, another Oxford astrophysicist on the team, emphasised what made this discovery so valuable. This is an object from a part of the galaxy we've never seen up close before. There's a 2/3 chance this comet is older than the solar system, and it's been drifting through interstellar space ever since it formed. It carries information from a region of the Milky Way that remains largely inaccessible to direct study. A frozen sample from the thick disk brought to our doorstep by the vagaries of gravitational interactions and cosmic chance. If the modelling is correct, 3I Atlas formed around an ancient star. That has implications for its composition. Stars in the thick disk are metal poor in astronomical terms, meaning they have less of the heavy elements that make up rock and dust. Comets forming around such stars might be particularly rich in water ice and other volatile compounds, because the lower abundance of dust means more of the mass in the forming planetary system gets locked into ices rather than rocky material. Hopkins predicted exactly this. Because 3I Atlas likely developed near an old thick disk star, it should contain abundant water ice. When it moved closer to the Sun, solar energy would warm the surface, triggering outbursts of vapour and dust, potentially creating a spectacular glowing tail. The swift observations confirm the first part of that prediction. The water is there and it's actively sublimating, albeit through the unexpected mechanism of ejected ice grains rather than direct surface sublimation. The observations also revealed that at least 8% of the comet's surface must be active, a surprisingly large fraction. Typical comets from our own solar system show active fractions of 3 to 5%. The higher activity level in 3I Atlas might reflect its age and composition, or perhaps it indicates the comet has been through less processing, fewer passes near stars that would have baked away the most volatile materials. As 3 Atlas continued its journey through the inner solar system, it approached its closest point to the Sun on October 30th, 2025. Perihelion, as this moment is called, occurred at a distance of about 203 million kilometers, roughly 1.4 astronomical units, just inside the orbit of Mars. This was the moment when solar heating would peak, when the comet would experience its maximum activity. Ground-based telescopes lost sight of 3I Atlas in early October as it swung behind the Sun from Earth's perspective. The solar glare rendered it invisible, creating a blackout window during the most scientifically interesting phase of its approach. But spacecraft positioned elsewhere in the solar system maintained their vigil. The European Space Agency's ExoMars Trace Gas Orbiter, in orbit around Mars, captured images of 3I Atlas on October 3rd when the comet passed within about 30 million kilometers of the red planet. Multiple instruments aboard the orbiter studied the comet's coma and tail, gathering data on its composition and behavior during a period when Earth-based observers were shut out. NASA's Mars Reconnaissance Orbiter also had an opportunity to observe, using its high-rise camera capable of incredibly high-resolution imaging. There has been some controversy about whether certain observations were conducted or released, with Harvard astrophysicist Avi Loeb publicly requesting access to images he believes were taken. NASA has not confirmed all details, and the scientific community awaits publication of the Mars-based observations. The James Webb Space Telescope was scheduled to observe 3I Atlas, again in December 2025, after perihelion, when the comet would emerge from behind the Sun and become visible once more. The Hubble Space Telescope planned ultraviolet spectroscopy observations in November to determine the composition of gas emissions and measure ratios like sulfur to oxygen, which could provide insights into the formation environment of the comet's parent star system. ESA's JUICE spacecraft, currently en route to Jupiter, had perhaps the best vantage point of any spacecraft for observing 3I Atlas in a highly active state. Observations using JUICE's suite of cameras, spectrometers, and particle sensors were attempted in November 2025, potentially in coordination with NASA's Europa Clipper mission. Both spacecraft carry twin ultraviolet spectrographs that could provide complementary data. The data gathered from all these observations, from space telescopes and spacecraft scattered across the solar system, will be synthesized over months and years to come. Each spectrum, each image, each photometric measurement adds a piece to the puzzle of what 3I Atlas is and where it came from. The implications extend far beyond a single comet. Interstellar objects like 3I Atlas are thought to be incredibly common in the Milky Way. Theoretical models suggest there might be more interstellar visitors than native solar system objects, with potentially trillions of these wanderers drifting through the galaxy at any given time. The reason we've only confirmed 3 is simple. They're usually too faint, too fast, and too unexpected for our current survey telescopes to catch. The Vera Rubin Observatory, which recently completed commissioning, promises to change this. Its wide-field camera and rapid survey capabilities should detect interstellar objects far more frequently, perhaps several per year once it reaches full operational status. In fact, the Rubin Observatory serendipitously captured images of 3I Atlas during its science validation observations from June 21st to July 3rd, just before the official discovery. If those observations had started 2 weeks earlier, Rubin would have been credited with the discovery instead of Atlas. Each new interstellar visitor teaches us something about the diversity of planetary systems across the galaxy. They carry chemical fingerprints from their birth environments, frozen snapshots of conditions around stars that might be vastly different from our own Sun. By studying them, astronomers can begin to understand how the processes of planet formation vary, with different stellar types, different metallicities, different regions of the galaxy. The detection of water in 3I Atlas in particular has profound implications for astrobiology. If water is common in comets throughout the galaxy, and if these comets regularly get ejected from their home systems to wander into stellar space, then water delivery to planetary systems might be a universal phenomenon. Comets could be the galaxy's delivery service, seeding young worlds with the essential molecule of life. Some researchers, including Suzanne Falsner and Michelle Bannister, have proposed that objects like 3I Atlas might even have played a role in Earth's formation. Imagine 5 billion years ago, an interstellar object similar to 3I Atlas, passing through the nebula from which our Sun was forming. Captured by the gravitational collapse of the swirling gas and dust, it becomes incorporated into the protoplanetary disk. There, it accretes additional material, growing into a larger body that eventually becomes part of Earth itself. The atoms in our bodies, the water in our oceans, might have arrived aboard an ancient interstellar traveller, a cosmic immigrant that found a new home in the solar nebula. It's a romantic notion, and currently speculative, but 3I Atlas and future interstellar visitors might help determine whether such scenarios are plausible. By understanding the compositions, sizes, and frequencies of these objects, astronomers can model how often they interact with forming planetary systems and what role they might play in delivering volatiles and organic compounds. The scientific community's excitement about 3I Atlas is matched by public interest, though not all of that interest has been scientifically grounded. Social media platforms have seen a wave of speculation, with some conspiracy theories claiming the comet is an alien spacecraft or harbouring some kind of threat. Physicist Brian Cox publicly denounced AI-generated deepfake videos that falsely portrayed him endorsing such ideas, calling them nonsense and thanking YouTube for removing the content. Cox described 3I Atlas more poetically and accurately as a message from a dead world. The comet, he emphasised, is a natural formation composed of carbon dioxide, water ice and cosmic dust, following a predictable orbit. It will pass the Sun and continue drifting through the galaxy, perhaps eventually encountering civilizations far in the future as a relic from our era. The universe's natural wonders, Cox noted, often outshine fiction. As 3I Atlas continues to fade from Earth's view, moving away from the Sun on its outbound journey, it will eventually become too faint for most telescopes to track. By early 2026, only the largest professional observatories will still be able to detect it. By 2027, it will pass Mars's orbit on its outbound leg, heading back toward the outer reaches of the solar system and beyond. When 3I Atlas crosses the heliopause, the boundary where the Sun's influence gives way to interstellar space, it will once again become what it was for billions of years. A solitary wanderer, drifting through the void, carrying its cargo of ancient ice through the darkness between stars. Perhaps, millions or billions of years from now, it will enter another solar system, where other astronomers might detect it, study it, marvel at this visitor that once passed through ours. For now, while it's still within reach, the scientific community is squeezing every possible drop of information from this remarkable object. Every spectrum, every measurement of brightness, every calculation of outgassing rates adds to our understanding. The water that Swift detected pouring from 3I Atlas, 40 kilograms every second, is more than just frozen molecules sublimating in sunlight. It's a revelation, a confirmation that the building blocks of life are woven into the very fabric of the galaxy. The universe is speaking to us through objects like 3I Atlas, sending messages written in chemistry and physics, frozen in ice that predates our world. We're learning to read that language, slowly, one interstellar visitor at a time. And what we're discovering is that we are not isolated, not unique. The ingredients that made Earth habitable, the water that fills our oceans and flows in our cells, exists in abundance throughout the cosmos. 3 interstellar visitors, 3 different stories. Oumuamua, mysterious and dry, possibly an asteroid or perhaps something else entirely, its nature still debated. Borisov, a pristine comet rich in carbon monoxide, offering a glimpse of chemistry from another star. And now 3I Atlas, 7 billion years old, pouring water into space, teaching us that expectations are made to be exceeded and that the universe has more wonders waiting than we ever imagined. If you've enjoyed diving deep into the mysteries of 3I Atlas and its ancient ice from another star, make sure to like this video and subscribe to Tales of Gravity for more explorations of the cosmos. Share your thoughts in the comments. What do you think an object 7 billion years old can teach us about the origins of life in the galaxy? Hit that notification bell so you don't miss the next journey through space and time. Until then, keep looking up and remember that somewhere out there, countless frozen messengers are drifting through the dark, each one carrying secrets we're only beginning to unlock.